Oh, hello. Good afternoon. So I have recorded 4 videos. This is the first one, practice problems that I was planning to do in today's review session for test 2. And unfortunately, or I don't know, fortunately, we missed that. So that's what I'm going to do. This is video 1, and this is about rational functions and graphing rational functions. So here's the problem. Problem is given in this form, and we're going to determine important components of the rational function, and it is also going to help us to graph it. That's what we will be doing. So let's start. Okay. So the first thing we do with the rational functions, we look at the wholes. So I put the question in that order. If you don't get to see the question in that order, please go ahead and find that part. Find the wholes first. So wholes occur if we are able to simplify exact same terms, numerator and denominator. And then we write the simplified version of function in this form, and it will help us to work through for the rest of the problem. So because we simplified x minus 3's, we make it equal to 0, and we say that at x equals to 3, function does have a whole. But x equals to 3 is a line, so we would like to see the whole with the y component. Okay, so like x and y, that's coordinate pair. So we're going to take that 3 and plug that into simplified version to be able to find the y component. So 2 times 3 minus 1 divided by 3 plus 1. And then that will give us 4 over 4, which is 1. Then we're going to say that, okay, we do have a whole occurring at 3.1, 3, 1. All right, so that's the complete answer. It's not x equals 3. You can get only half credit for that because we want you to figure out where is the whole located. The whole is located at 0.31. All right, vertical asymptote. Vertical asymptote are the values that is going to make the denominator 0. So a denominator with the simplified version is x plus 1, so x cannot be equal to -1, which means that, I know this is awkward, because x cannot be equal to 1, at x equals -1, because x cannot be equal to -1, at x equals -1, we do have a vertical asymptote. That will be the complete answer. So we know the whole, we know the vertical asymptote. Those two are the elements that function cannot take. They are the protectors of the function. One of them protects the function as a whole when we simplify it, numerator and denominator with the exact same terms. The other one is the leftover after the simplification. If simplification occurs, that is going to make the denominator 0, and that's an equation of a line, -1. So now we can talk about the domain. So domain are going to be the values excluding whole and vertical asymptote. So we need to exclude wherever the whole and VA is, and that's going to become our domain. So whole was at 3, vertical asymptote at -1. So then we will come in -1, negative infinity to -1, -1 to 3, union 3 to infinity. So now at this point it should make sense to you because these are the vertical asymptote points and these are the whole points. Okay, so then we need to exclude them at our domain. All right, keep going. So that's the full answer for the domain. Now x-intercepts. X-intercepts are the values that is going to make the numerator equal to 0. Only numerator. Whatever value is numerator is equal to 0 in the rational functions, that will be the x-intercept. And which numerator? The simplified version. Okay, simplified version. What do we have on the numerator? X minus 1. So then we're going to say that at x equals 1, we have 1 x-intercept. Okay, so then we need to write it as a point. When x is equal to 1, y will be equal to 0. That will be the answer. Okay, we're going to look at the values where the numerator is equal to 0, because denominator cannot be 0. Okay, now y-intercept. Y-intercept are the values when we plug into 0 to the function, and we will be plugging into 0 to the function with the simplified form, which will be 2 times 0 minus 1 all over 0 plus 1. Then that will turn out to be negative 2 over 1. So then y-intercept will become 0, negative 2. Okay, so a couple of things important here in general, guys. Intercepts and holes are points. Please try to give them as point values. Domain as an interval. I'm going back to the question. Holes occur. You start by solving the holes. Holes occur when we do have exact same terms on numerator and denominator. We simplify them. As soon as we simplify them, we identify that at that x value there will be a hole, and we create the simplified version of the function, and we will work through the rest of the questions with that form. Now the last thing, horizontal asymptote. So for horizontal asymptote, we look at the numerator and denominator degree. Okay? So if the degrees are equal, we just divide the leading coefficients. So let's write it this way. If the numerator and denominator equal degree, so divide the leading coefficients, and that will be the horizontal asymptote. Okay, if numerator has a greater degree than denominator, then there is no horizontal asymptote. There will be a slant asymptote, which we will see in module 3. And the last portion, let me see if I can enter something line here. Let's see. Yeah, I can do that. And if numerator has a less degree than denominator, all right, and then we do have a horizontal asymptote y equals 0. So if we go back and look at our case, we can look at the original function, right? So in the original function, we do have f of x equal to 2 times x minus 1 times x minus 3 all over x minus 3 x plus 1. So here we're going to have some x squared degree when we FOIL it out, and do not FOIL it out, but just know that because you're multiplying with the first degree and the first degree. And here we're going to have some x squared degree and some other million terms, but we're not interested in. So the leading coefficient 2 here, there's a hidden leading coefficient 1 there. So then 2 over 1, y equals 2, that will be the horizontal asymptote. All right. So now we're going to use all this information and we're going to try to draw the graph. So what do we have? We do have 3, 1 hole. So x is 3, y is 1. We do have a hole. All right. We have an x-intercept at 1, 0. We do have y-intercept at 0, negative 2. Okay. We do have horizontal asymptote at y equals 2. Okay, we do have a vertical asymptote at x equals negative 1. All right, so one portion of the graph is on the fourth quadrant. I'm saying that this will be our first, second, third, and the fourth quadrant. So this vertical and horizontal asymptote create the new quadrants, new coordinate system. So we're going to have one portion of the rational functions, not like that. Okay, so what do we know about the rational function? This is the parent rational function, and the shape is like this, right? If you go ahead and plug it in Desmos, let's go ahead and do that if you want. Alright, so start graphing. I'm just trying to show you something that you can try, but we want you to also know how the functions, parent functions look like. So 1 over x, right? So this is the parent function, 1 over x. And if you have positive, positive, so the other one should be positive. Positive means that you have a positive term on the numerator and denominator. So once we got this portion, it's going to be exactly opposite portion of that, like this one, right? So we cannot have a portion here or portion there. Or you might want to go ahead and try some values here. I've tried and found one, -3, 4. If you want, you can give a couple of points, like -3, 4 will satisfy this, and then we can have the function like that. So this is first video about drawing rational functions, going over each and every important component on it. Hope this helps.